So anyway, let me get on with this. We just had a wonderful dinner with Gabriel, and he came to us from Colombia, and he had his original. I guess some of the guys that he had worked with, that he works with now, have been up here before. So we had Chuck. What's Chuck's last name?
Haley.
Yeah, Chuck Haley was up here before. So just a fascinating guy. Kirsten Perez, who has been here at least 3 times. So she works on New Star, and she's working now with Gabriel and on these projects. So it's just great. And so they're all back, and Kirsten was up in at MIT. Now she's back, and as you said, that Chuck had poached her for to come back to Columbia. So it's just wonderful. So hopefully we'll get Kirsten again back too. But Gabriel is a PhD candidate studying particle astrophysics, and his interest in uncovering the dark secrets of the universe came as no surprise to any of his friends and family, and or the public school educators that shaped his path, all of whom bore him to discovering video games through the NASA website and spending his Saturdays computing the entropy of plasma waves. Don't we all? Yeah. I mean, so when he isn't lost in programming simulations or integrating SILI, is that how you go that? Silly detectors into the GAPS experiment, he can sometimes be found mixing some craft cocktails, which makes him an asset in and out of the lab. So please, won't you welcome, for the first time here, Gabriel Bridges. Gabriel?
Wow. Well, thank you so much for having me. It is a thrill to be here. As mentioned, I'm Gabriel. I'm in the last year now, actually, of my PhD, so beginning to work on my dissertation, which will in large part be about this beautiful monstrosity next to me in this photo, which is GAPS. GAPS is a balloon-borne experiment that's set to be launched from Antarctica that's venturing off into space to hopefully hunt down signs of dark matter. But before I can tell you about, the 6-year journey that took me to this place, I want to start by, of course, talking a little bit about what dark matter is, going over the science of that. I'm a little bit embarrassed now because, of course, I just saw these incredible photos of galaxies, and I have a much more mundane one maybe to show you. But for the time being, I'd like all of you guys to pretend for a moment with me that you yourselves are astrophysicists. Might be a little bit easier for some than others. And this is maybe a new image that you and your colleagues are poring over. There's a ton of rich scientific detail in an image like this. First of all, I guess most obviously perhaps are the hundreds of millions of stars. So if you're, say, an astrophysicist interested in stellar evolution, you have a large sample to look across here to study the details of how stars grow and maybe eventually die. You'll also probably notice some of these darker patches. These are massive clouds of dust and gas, and they don't look like a lot on an image like this, but if you switch up and look in at at lower wavelengths into X-ray and gamma ray, some of those clouds will light up, and they light up because as dense blobs of dust and gas, they're great targets for very energetic particles. So we can study those and understand more about some of the most energetic things in galaxies and out there in space. You might notice as well that some of those dark clouds turn here into these bright, vibrant, hot pink spots. That's because clouds that get dense enough turn into star-forming regions, and the newborn stars at the heart of those become very hot and ionize the surrounding gas, turning it into a brilliant pink plasma. So you and your friends are probably divvying up what parts of this you're going to look at, but you're interested in the bigger questions about galaxies. You're not going to worry about the stars here or the dust. You want to know about galaxy formation and evolution, the structure of these things. And there are some open, interesting questions today. Even recently, JWST is now finding galaxies that are older than we previously thought possible. So there very much are things worth studying about how these systems form. And if you're going to do that, really what you're trying to do is trace through the history of how stars gather in galaxies, how they move through them. And so you're going to want to do a lot of study of the kinematics of systems like this. You're going to look and try and figure out what forces are pulling on things in the galaxy and how are they moving. So there are 2 ways we can approach that. From the forces side of things, we do know that basically the only game in town for a galaxy is gravity. And so we need to figure out how much mass is in the galaxy, where that mass is, so we can figure out how it's pulling on the stars that are in orbit. And luckily for us, most of the mass in the galaxy comes from its stars, and stars have a very clear relationship that's well understood between how massive they are and how bright they are. So really the question of where is the mass in a galaxy like this boils down to where is it brightest. And you'll notice immediately here at the very center, very, very bright. Here at the very edges, not very bright. So you can go around, pick up little patches, measure how bright they are, and figure out how much mass is in that little bit of the galaxy. For velocity, we're also a little bit lucky. There's this fun little effect called the relativistic Doppler shift, which basically says that as something moves towards you, the light from it will get a little bit more blue, and as it moves away from you, it'll get a little bit more red, and how red and blue it gets depends on how fast it's moving. So if you go and take your camera and look at the light coming from all the stars in this image, and you measure for each star how blue or how red it is, how will the blue or red shift, I should say, you can measure directly its velocity. So we can study this in detail and hopefully figure out what's going on inside of this galaxy and what will happen to it over potentially billions of years. And here are our results. This is real data matched to this galaxy. So on the bottom here, I'm showing you how far we are from the galactic center, roughly lined up with where it actually is on this image. And the y-axis here is showing you how fast things are moving. First of all, off this yellow line here, this is what you might imagine is our prediction, the expectation based on that measurement of mass. So what you're seeing is initially, if you're very close, if you're at the dead center of the galaxy, you're not going to move at all, of course. You're not orbiting. The whole galaxy is swimming around you. And as you start to get farther away from the center of the galaxy, at first you get faster and faster and faster. That's because as you move out, there's more and more mass that you're seeing. There's more and more mass pulling you towards the center of that galaxy, and that's going to cause you to spin faster. But at some point, and looking at this image, it sort of makes sense when you're kind of around the halfway point. This is roughly 10,000 light years away from the center of the galaxy. You turn around, and that's because there's another effect, which is that you're actually going to slow down as you get farther from the center of the galaxy, or farther from a center of mass, right? We know that Earth orbits the sun roughly once a year, but Uranus takes more than 100 years to orbit the sun. So you generally slow down as you get farther away. And as you're way out here, right, when you're talking about the stars at the very distant edges where there's not really much more galaxy for them to see, they're already feeling the full force of the entire thing, all that's left for them to do is to get farther away and therefore slower. So that yellow line makes a lot of sense. It lines up very well with what we're seeing in this image. But then you might notice this pink line, or the pink data points here. These are the actual velocity measurements. And you might start scratching your head and saying, well, those don't look anything like the yellow line. Well, what's going on? And there's in fact a big issue that they don't look like the yellow line, because if it's true that a star out here is moving at 130 kilometers a second, but it's only feeling gravity enough to cause it to orbit at 50 kilometers a second, well, then that star isn't bound to the galaxy. It's not hanging out, it's flying right by. So almost all the stars that we've measured in this galaxy should be tearing their way through space, and this galaxy should disappear in a few thousand years. But there's galaxies everywhere, so we know that can't be true. Something must be up. So what else could be going on? Well, maybe we were wrong about the relationship between a star's mass and how bright it is. Maybe stars are actually more massive than we think they are compared to their brightness. If that were true, you could take this whole yellow curve and stretch it upwards. And maybe you will wind up with predicting some speeds that are in this 120, 140 kilometer a second range. But you can't, with that adjustment, do anything about the shape of this curve. It will still turn over in basically the same place, and you will still see everything start to get slower and slower, farther and farther out. So maybe you can make this part of the galaxy stable, and you only have to worry about losing all of the outer edges. But that's also not what we observe when we see galaxies. The only way you can rectify these curves is if you say that there must be additional missing hidden mass in the galaxy that isn't where we see all the stars. And it's got to be a lot. It's got to be so much that as we go farther and farther out, we're continuing to see more and more mass, so that the amount of mass we're adding to the galaxy as we get farther away from it is overcoming the fact that we're getting significantly farther from the center. And this basic observation is made first by the now famous astronomer Vera Rubin in the 1970s. And she at the time coins the term non-luminous matter to refer to this stuff that obviously we can't see in an image like this, but must be there to explain how fast stars are moving in galaxies, to explain, in fact, why galaxies are stable at all. And today we call that dark matter. One of the other remarkable things that I've hinted at this point, but will now make explicit, is it's not a small amount of mass. If you want to explain how fast things move in galaxies, if you want galaxies to actually be stable structures that hang around for us to look at today, 85% of the mass in a galaxy has to be dark matter. It cannot be contained in the stuff that we can see in an image like this. And so that's a really big revelation, and it's a pretty exciting one. And it opens the door for a lot of new discoveries and new investigations. If we flash forward a few decades, we get some more sophisticated techniques. As it turns out, in general relativity, gravity isn't this force, it's the bending of space and time. And that's pretty cool, because what that means is that massive enough objects actually will bend the path that light takes through them, kind of like a lens. In fact, sometimes it's proposed that we can use the gravitational lensing of our sun to make a telescope with an unparalleled focal length and see surface details of exoplanets, but that's a little bit of an outlandish idea. For the time being, what we can do with this is go out there into the universe and measure how much light seems to be warping around massive objects like a galaxy, and use that to independently measure the mass of that galaxy. And when we do this for isolated galaxies, we find results that are consistent with what we saw from the rotation curves. About 85% of the mass seems to be non-luminous. But there's a really good advantage that you have with gravitational lensing that's not just this independent mass measurement. You also can see where the mass is located for very large objects. And so this is a very famous example of it. It's one of the critical pieces of evidence we have for dark matter. This is the bullet cluster. And what the bullet cluster is actually two galaxy clusters that a very long time ago smashed into each other. Now, in a galaxy cluster, most of the mass is actually held in gas. And so when those galaxy clusters smash together, that gas runs into itself, gets stuck together, and heats up a lot, right? These are traveling at incredible speeds. And this pink image in the middle is actually an X-ray image that is showing you roughly where all of that gas is. You can even see this little shape here is where the bullet cluster gets its name. This is a shock wave caused from one of those galaxy clusters tearing through the other one. So the pink you can think of as tracing out basically all of the visible mass in the galaxy. The blue, on the other hand, is showing us where the gravitational lensing is the strongest. So this is telling us not just that there's a lot of extra mass in the galaxy we can't see, but it's in a different location to the visible mass. So once again, there's not really like some sort of weird calibration issue with how visible mass produces light. There seems like there's a distinct other mysterious substance in these structures, in galaxies and galaxy clusters, that is responsible for a substantial amount of the mass. And in fact, if you go through and do the math and ask yourself, well, how much mass must we add to shift the center of mass of this galaxy away from the gas and towards the blue region out here? It's about 85%. Finally, we're going to turn to our cosmologist friends. They're a little bit weirder. They like to take pictures not of individual galaxies or even galaxy clusters, but of the entire universe. And this here is kind of like a baby photo of the universe. It's relic radiation from the Big Bang. This is as close as we can see to what the universe looked like moments after its creation. And this probably looks to you pretty noisy and maybe not that interesting, but what I want you to do is imagine that this is actually the surface of a pond in the middle of a rainstorm, right? The surface, you know, is going to be very choppy and chaotic. But we also know that if you have a nice still pond and put a single raindrop into that, you get a nice little understandable circle, a little ripple coming in. It turns out you can take some fancy mathematical and statistical techniques to an image like this and decompose it into all those little circles. And you can figure out how many of a certain size exist. And that tells you something very detailed about the beginning of the universe. And in particular, the pattern revealed when you do this tells you that at the very beginning of the universe, about 85% of the mass in the universe wasn't really interacting very much at all. About 85% of the mass in the universe at its very beginning was dark matter. And so to put all of this together, the key thing I want you to take home is that when we talk about dark matter as scientists, we're not really looking for it in terms of discovering it. It's already out there. We know for sure. It would be too strange to imagine these entirely disparate methods of measuring properties of the universe to all point you to the same thing if they weren't a related and continuous phenomena. As far as we're concerned, the best explanation for the most data we observe in the universe is dark matter. We just don't know what it is. And that's killing some scientists. But we have learned a few things from looking out there in the universe. Because we know that it must have been there in roughly the same concentration at the beginning of the universe as it is today, whatever dark matter is has to be stable. If it was some radioactive isotope and decaying over time, we would know that. Now, it can still decay, it just has to have a half-life longer than the age of the observable universe, which, to be fair, there are some radioactive isotopes that do. And that's very important because we do look for evidence of dark matter that might be decaying. We also know critically that dark matter must be, whatever it is, must be massive. It must be a massive particle because all of the evidence we have for it comes from the way it gravitationally interacts, and things that are not massive do not interact with gravity. And finally, we know that dark matter, of course, almost by definition, cannot interact with light. Otherwise, we would have seen it with any number of our telescopes. Remember, it's 85% of the mass budget of the universe. So if it was making even the littlest bit of light, we would have found it. And so with that in mind, we're going to ask the question, well, what can dark matter be? And that's going to take us to our particle physicist friends. They've got this neat little thing called the Standard Model of Particle Physics, which they will say sort of correctly explains everything we know and observe in the entire universe. And you can think of this sort of like the periodic table of elements, but for subatomic particles. So really, we think everything in the universe is made from these guys. So if you're looking for a particle that can explain dark matter, it's somewhere in there. But let's run through those properties I just talked about. First of all, it's got to have mass. The gluon and the photon are out. These are force carriers. The photon actually, of course, being responsible for light. So can't be them. Next up, it can't be charged. That's going to wipe out most of the table here. If it was charged particles, charged matter interacts with light by definition. So those stuff we would see. They would be visible to us. It's got to be stable. There goes the Z boson and the Higgs boson, which you've probably heard of. Was a pretty major discovery. Can't be those guys. This leaves us only with 3 strange particles, the neutrinos down here at the very bottom. The neutrinos are interesting and they're worth researching, but we know that they can't be dark matter. And the reason they can't be dark matter is that, firstly, we actually know how many neutrinos there were at the very beginning of the universe. We know how many there are today, approximately. It's not 85% of the universe. It's a fraction of a percent. So there's not enough of them out there to actually explain dark matter. The other thing about them is the neutrinos that do exist all move at about the speed of light. And the problem with that is if you want dark matter to collect enough to be the basis upon which galaxies form, you can't have it traveling around at the speed of light. It's going to run away before the stars ever have a chance to form. So the neutrinos are out. And now you might notice a small problem, which is I've eliminated every single thing in the Standard Model of Particle Physics. But one man's trash, another man's treasure. The really exciting thing is I've eliminated every single particle in the Standard Model of Particle Physics. That means that whatever dark matter is, it's not just some weird quirk of galaxies. It's not just some strange, unresolved astrophysical question. It's a question that asks us about the fundamental nature of reality, the fundamental physics of our universe. To figure out and to answer the question what dark matter is isn't just about galaxy formation anymore. It really is about our fundamental understanding of physics, and that's a very exciting question to be working on. Of course, such an exciting question is going to get a lot of attention, and the first attention it's going to gather are particle theorists. They're going to start to come up with all kinds of ideas for what dark matter could be. So I've shown a few of them here with how massive they are, and I'm putting up here a few of those particles I mentioned it can't be, just to make this point that where we start is kind of in and around the range of masses that we're familiar with for particles. My mass unit here is a GeV. We're not going to worry about that too much for now. But just to name a few, we've got the gravitino. This comes from supersymmetry. We have the sterile neutrino. This is, imagine you wanted the neutrinos to be dark matter. You can kind of make some fun counterparts to them that don't interact very much at all, but could be dark matter. More fun, we have the WIMPs. That stands for weakly interacting massive particle, or universal extra dimension theories. There's a bunch of weird ideas they're coming up with. But one by one, we're not finding necessarily anything. And the theorists, they can just sit down all day, do their little calculations, keep spitting out new ideas for what it could be. And they go a little bit crazy So we've zoomed out a little bit now, and we have weirder things on here. We have quark nuggets, we have fuzzy dark matter, and critically, we're spanning now 54 orders of magnitude in terms of the mass of this particle, 70 orders of magnitude if we want to go all the way up and talk about primordial black holes, which I do, but that's a whole other talk in and of itself. Really, what I'm trying to say here is we have no idea what dark matter is, and we have proposed something that spans well beyond the realm of particle masses we even observe anywhere in the universe today to try and explain it. And in fact, if you want to zoom out even more, here is a pretty typical map you might see of all the possible theories that people have proposed to explain dark matter. There's a lot of silly names on here I'm not even going to bother listing out. Anything in the bright region here, currently experimentally viable. Every single thing in here could be dark matter. We have not yet ruled it out. And so really all I'm trying to say is that if you want to know what dark matter is, you shouldn't ask the theorists because they have a lot of answers for it, but not a lot of evidence. Today, dark matter really is almost a purely experimental question. We have a ton of ways we could explain it, but we just don't have evidence to describe what exactly it is. And so really the challenge is, how do we search for dark matter? And there are a few techniques. The first of which I'm going to dub make it. You can produce dark matter. So this here is an image of the Large Hadron Collider, the most powerful particle accelerator we've ever made in Switzerland. It's actually one of the premier experiments there, Atlas, which, just to point out, there's a person down here for scale. It's a massive experiment. They smashed together particles at roughly 13.6 TeV. A TeV is an energy unit. It's roughly the energy of a mosquito flying around. So if you've ever had a mosquito run into you, that's a TeV of energy. But in this case, we're concentrating all that energy down into a single subatomic particle. So maybe not a lot of energy for a mosquito, a lot of energy for a fundamental particle. We smash them together at those energies, and then we look with giant detectors like this to figure out what popped out when they smashed together. This is how we found the Higgs boson. It's how we found most of the particles in the standard model of physics. And so the idea is, well, you keep doing this over and over and over again, and eventually, it might be very rare, but a dark matter particle might pop out, and then you would be able to measure it. Well, they haven't found anything yet, which is a small problem. One of the reasons why they might not have found anything is that, as I said, it's operating at 13.6 TeV. So if dark matter has a mass of 13.7 TeV, they're not going to see it. And there's a whole lot more masses that dark matter could have, anything up to 10 to the 40, then you can actually explore with something like the Large Hadron Collider. The other problem, which is a bit more of a philosophical one, is that all of our evidence for dark matter actually comes from astrophysics. It comes from galaxies and the universe at large. So if you make dark matter down here in one of your labs, you're not really sure that what you've made explains the astrophysical dark matter we've seen. And so with that in mind, we're going to move on. You might say it's kind of silly that we're taking the sort of 15% mass of the universe to try and make a bit of the 85%. Like if 85% of the universe is dark matter, of course, it's around us all the time. So why are we trying to make it when we could just catch it? Or in this case, shake it. Shake it here referring to typically a xenon atom. So this is direct detection. This is an example experiment. It's called Xenon. It's one of the premier ones. And it's buried deep underground in a mine in Italy. Deep underground so that normal particles, the ones we see in the standard model that are coming in from space, get stopped by the mountain above it. And so the only thing in principle that should be entering this tank deep under the mountains is dark matter. And we're going to sit there, we're going to fill up this tank with liquid xenon, and we're going to sit and we're going to wait, and we're going to look at it very, very carefully. And in principle, all the time, dark matter is streaming right through this tank. And every once in a while, a dark matter particle might smack into a xenon atom. And when it does, that xenon atom will recoil, shedding off a few electrons, giving off a flash of light, distinct signals that you can detect to infer that a dark matter particle must have traveled through your experiment and infer properties about the particle from that. So that's really good. It's a great experiment, and it's found nothing so far. The only thing it's actually seen are a few neutrinos, which can also make it deep underground. But that's kind of a problem because we already know about the neutrinos. They're already out there. We know they're not dark matter. And so once you start to see them, you're going to start to drown out signals you might expect to see with those neutrinos instead. And so finally, we're going to return, we've done our little adventure into particle physics, back to the astrophysicists. See, there's two things about astrophysics. First of all, an astrophysicist hates not finding something. In astrophysics, signals are easy to find. You guys do it here every day when you take a photo of the night sky. Those are countless signals from stars and galaxies. And so why should we spend all our time not finding things when we can instead look for things that are actually out there? The other thing is, I made the argument going from collider to underground experiment that, well, why bother trying to make dark matter when it's all around us? The same argument applies here. Why bother waiting for all this dark matter all around us to eventually interact in your small little liquid tank of xenon, when you can just wait for dark matter to interact with other dark matter? We can, instead of having a small tank of liquid xenon, have a volume of the observable universe into which we can have these interactions. And so what we're going to look for instead are distinct and unique signatures from those interactions. We're going to let dark matter interact with other dark matter, typically phenomenologically undergo an annihilation, and then produce interesting things that are easy for us to detect instead of doing all this hard work. So the first experiment that's done something like this is Fermi. Fermi is actually a gamma ray telescope. It's generic, not just for dark matter, and it's done a lot of incredible work. It sees the entire night sky in gamma rays. And when you focus in not on the entire night sky, but just on the center of our galaxy, you see something that looks like this. This is a spectrum, and it's showing you roughly how many gamma rays we see at certain energies. And the thing you'll notice here is that there's this roughly straight line that travels through it. That's the astrophysical background. It's kind of what we expected we would see. But there's also this big bump. And that's a weird little bump to see. It's exactly what one might expect if there was a bunch of dark matter sitting in the center of our galaxy, which we expect there to be, interacting and annihilating. And in this case, that dark matter would have a mass of about 28 GeV. So that's great. We did it. We found dark matter. We figured out what it is. We can all pack up and go home, right? There's a bit of a problem with the galactic center. It's a very dense, busy place. It's filled with so many stars. It's so bright that it's actually hard to pick out individual things in there. So you can hide a lot of really interesting and exciting and sometimes exotic stars that, while fun to look at and analyze, are not dark matter. And in particular, one type of star, shown here in this little artist's rendition, the millisecond pulsar, is a copious producer of gamma rays, and in fact could produce the gamma ray signature that Fermi has observed. So we can go out here and find all these nice little signals, but then we get stuck trying to cleanly connect them back to dark matter because you have other things produce them. The other experiment that's found some signals is this. This is AMS. It is a particle detector on the International Space Station. It uses a giant magnet to collect and identify cosmic rays that travel through it. Its major signature is the positron signal. Positrons are the antiparticle of an electron. And you can see here that same thing, the spectrum, the number of positrons we're seeing at different energies. The same story. There's this little gray curve here. This is the diffuse term. That's the astrophysical background. It's what we expect to see. And in fact, the positron spectrum here is dominated not by that background, but by some as of yet unidentified source of positrons. Well, what could make positrons? Annihilating dark matter could make positrons. It can make tons of them. But you can also make tons and tons of positrons using something called a pulsar wind nebula. And in fact, the most recent analysis of this data has pointed out that if you just use the pulsar wind nebulas we know about that are close to Earth, you can fully explain this spectrum. So in both these cases, we kind of have the same problem. We did go out there and find signals, and we found signals that are easy to identify. But we then struggled to connect them cleanly back to dark matter. Because when you choose a signal that's easy to identify, you typically are also choosing something that's easy to make. And so if you really want to make progress in indirect detection, which is what these experiments are doing, you want to find some perfect target, some particle out there that you would be easily, readily able to identify, but which couldn't really be produced by any of these other things, no matter how exotic they may be. We want to avoid getting caught up worrying about where the particle came from. And so, does such a particle exist? Yes, it's called the antideuteron. If any of you guys follow fusion power, you might be familiar with deuterium. Deuterium is an isotope of hydrogen made from a proton and a neutron. An antideuteron is the antiparticle to that. It's an antiproton and an antineutron. And antideuterons are very massive. They're very hard, almost impossible to produce astrophysically. The only known mechanism for production is when very, very high, very highly energetic cosmic rays smash into diffuse gas in the interstellar medium. And the problem there is already there are very few cosmic rays with enough energy to produce antideuterons to begin with. And because those collisions are so energetic, the resulting antideuteron is also energetic, which is what you're seeing here in the blue curve, which is our astrophysical background. It's very, very low at low energies and peaks up here at a few GeV. By comparison, you have on here the red curve. The red curve is what you would expect to see from an annihilating dark matter particle. And you can see that while at high energies, they're comparable, at low energies, almost all your antideuterons are going to come from dark matter. And we know of no other mechanisms that could produce antideuterons. And so this is the vision for GAPS, is we go out there and we look specifically, very specifically for antideuterons. You can see here this black bar, that is the sensitivity of GAPS. So when GAPS does fly, it will be able to see antideuterons if there are more of them than this black line, and it won't see anything if it's less than this black line. So you can see clearly we're not sensitive to the background. If we see even one antideuteron, the odds are 1,000 to 1 that that antideuteron did not come from the astrophysical background because GAPS is not sensitive enough to even measure those antideuterons. So when we find them, we can be very certain that they must have come from something different, something like dark matter. Now, when you do this, you're doing what's called a rare event search. You're looking for a very rare particle that you almost don't expect to see, but that would, if found, give you a lot of information. And that puts some interesting design constraints on your experiment. Your experiment needs to be very big because you want to collect as many particles as possible, right? You're trying to find a particle that might only exist 1 in a billion. So you need to collect as many as possible. But you also need to have excellent discrimination power lest you get confused and think some particle that's some ordinary boring particle is the antideuteron you're looking for. And so these are two very challenging things because, of course, as you make your experiment bigger and bigger and bigger, you get more and more of those other boring particles, and you need to be able to reject them. And so GAPS, the way we search for dark matter, is with this new novel detection technique that's based on the formation, decay, and annihilation of exotic atoms. So I'm going to walk you through a little bit of what that looks like, but this here is my cartoon of the GAPS experiment. So first, I'll talk you through the two things we're going to talk about right now, which are the two subsystems that make the experiment work. In blue, I've shown the time of flight, which itself is broken up into the umbrella, cube, and cortina. This is responsible for measuring the time of flight of particles as they enter the experiment. So here's an antideuteron. It travels in. It first goes through the umbrella, which you can see here, sits about 1 meter above the rest of the experiment. It then hits the inner cube, which is down here. And because we know how far apart those are, and we know the time it took for the particle to travel, the time of flight, we've now measured its velocity. So as soon as a particle arrives, we know how fast it's going. After that, it enters the next part of the instrument, which is the silicon tracker, SILI tracker. The SILI tracker is made up of 10 layers, 36 modules a layer, 4 detectors per module. So you can imagine it's a dense cube filled with these sensitive silicon detectors that track the particle. So as a particle hits that detector, it gives you a little signal. That signal tells you how much energy the particle left behind in the detector, and it will slow down as it travels through them until it comes to a stop. That means we can now go back and count up all that energy and say how much energy did the particle have to begin with, because it's left it all behind in our instrument. And you might remember from high school or college physics that there's a clear relationship between the energy of a particle and its velocity. They're related by the mass. So once we've done this, we've made our first identification of the particle. We've measured its mass. Now we're going to follow that up by forming what's called an exotic atom. Now, an exotic atom is an ordinary atom where you've replaced an electron with something different, anything different. And in our case, that is the antideuteron itself. An antideuteron, being made of an antiproton, will be negatively charged, just like an electron. So the silicon atom it's come to a rest next to will see this as a very, very massive electron. And that will quickly lose energy in the atom, giving off specific line emissions. Just like an atom does when it's excited. If you've ever seen a gas discharge tube and you've looked at it with the fun spectral glasses, you'll have seen the distinct lines. The same thing's happening here, but because our particle is so much more massive, the lines are much more energetic. In fact, they come out as X-rays. And those X-rays have very unique energies, which are defined by the mass and charge of the particle. So if we can catch one of those X-rays and measure its energy, we can also identify what particle entered our instrument. And in fact, one of the most special things about this experiment is that our custom-built silicon detectors have the energy resolution to distinguish those specific X-ray lines, but also the dynamic range to measure the much larger energy deposition you expect from a slowing down particle inside the instrument. Finally, we're going to wind up with an atom, well, an atomic nucleus, really, that has an antideuteron in a tight orbit around it, very close to it. And for those of you familiar with antimatter, you know what comes next. There's an annihilation. The antideuteron will meet the regular matter of the atom, and they will destroy each other. In that destruction, you will produce a shower of new particles. And the number of particles you produce is related very strongly to the number of particles that went into the system. So an antiproton, when it annihilates, will make about 3 new particles. An antideuteron about 6, antihelium about 9 or 12. Here I'm just counting the number of subatomic particles, the protons and neutrons that make up these antiparticles. And so we have a third way now of identifying it. So you put all this together and you get very clear signals that look different depending on what particle entered your instrument. So this is that discrimination power I was telling you about. You might get a bunch of antiprotons. You might expect, and we do expect, to see way more antiprotons than antideuterons. But we'll see almost no antiprotons that produce the same set of signals that an antideuteron does. So we can very clearly distinguish between them. Now, an important point here, both for how the instrument operates, is that and part of its power is that, of course, we don't actually see those nice lines when they come in. We just see the parts of the instrument that turned on here. So we get an image that looks a little bit more like this. And it's our job to reconstruct the event. We go back through and draw lines and see how do we think things behaved when they entered our instrument. But this also reveals a really critical thing. If I imagine that instead of an antideuteron, I had a regular deuteron, so no antiparticle, no exotic atom, no annihilation, this is what you see. And this part of your path is identical. You'll lose the same amount of energy, you'll measure the same mass, but you won't get any of these extra products coming out. And so all I have to do to readily reject anything that isn't an antiparticle is just say I need to have a certain number of hits in my instrument. A certain number of parts of my instrument have to have turned on. They have to have measured a signal. And in fact, in flight, this is how we work. We have a complex trigger mechanism that only records data when many parts of the time of flight system are activated in a given event. And that means that already at a basic level, we don't have any data from particles we don't care about. We wind up only seeing these interesting and exciting antiparticles. This is how we thread that needle between having a very large instrument that is likely to actually collect an antideuteron, even though they're very rare, while still being able to very clearly identify and distinguish between antideuterons and the more boring particles. Now, this next part is really exciting for me because this is hot off the presses. This is actually something that I finally got working yesterday. This is real data from our instrument. We haven't flown yet, so we're not seeing antiparticles. Here we're seeing more boring cosmic rays, muons, that are interacting in the instrument. But you can see actually what the data will look like when we get it in space, and you can see exactly happening what I just described. Down here, you're seeing the actual raw instrument data, so just the parts of it that turned on. And up here, you're seeing reconstructing what happened. So a muon entered our instrument, came down through the TOF, stopped inside of our instrument, and kicked off a secondary particle that traveled this way. Now, on Earth, we don't have events that are nearly as exciting as the antiparticles, but we are already able to make sure that we're able to reconstruct those. And so this is really exciting, maybe more for me than you guys, but the instrument works. Anyway, With that, I'm going to move on to maybe the more fun part of the talk, where I talk about what it actually takes to build such a monstrous instrument and the journey. I'm going to start here where I really began in large part, which is when we began to actually construct the final experiment in 2022. But it is worth noting that the first paper published by the GAPS collaboration, which was a paper about the concept of GAPS, came out in 2002. And of course, the idea for this existed as a twinkle in the eye of my advisor for longer than that. And so I just want to say that, you know, a project that is this ambitious is a multi-decade long endeavor that touches on countless people, many of whom I don't have the privilege of being able to show in these photographs or even really talk about. So I want you all to keep that in mind, that there's, of course, a silent and invisible audience of people here who have worked tirelessly to make this project work. But the final journey, the final sprint to the finish line begins for us in March of 2022 at a facility at MIT. We were delayed by COVID, of course, for initially beginning construction, and we wound up at MIT simply because it was the first facility to become available to us when universities began to restart their in-person endeavors after COVID. Down here, you can see a couple of our engineers from JAXA, the Japanese Space Agency. They designed the thermal system for our experiment. I didn't mention this yet, but the tracker part, the silicon tracker, the center of our experiment, has to be kept at -40°C to operate. So we have a very sophisticated system, which you can see on the right here, of tubes that run through the tracker and carry with them refrigerant that we cool using a giant 8 square meter radiator that points into space. But they're here, along with Meng Zhao, a professor now in China, constructing the first pieces of our experiment, the basic gondola frame. And this is literally a photo from day one when it arrived at Bates, ready to be assembled. So for 6 months, I moved to MIT and lived there and worked there, tirelessly putting together the tracker, until, in anticipation of launching in 2023, we shipped across the country to UC Berkeley. We have a lot of electrical engineers at UC Berkeley, so the plan was we ship the whole thing across the country to our electrical engineers, who can then work from home but put together all of the electronics for us, so we'll be ready to launch in winter of 2023. At UC Berkeley, we finished putting together the tracker. This is the first row of the last layer. I have a couple fun videos on my phone that I didn't include of us actually putting in the last screws to triumphant music and cheers. We also here, you can see, begin to actually install all of the final flight-like electronics. And I included this image just to point out as well, one thing they don't really tell you about experiments is that they're 90% cables. It is the greatest agony that almost everything we do, the longest by far time commitment we have is the cable routing every time we try and put this experiment together. And you can see even more of those sitting on top. This is the first TOF panel to arrive, and us installing, finally integrating a complete and operable instrument, which began a long calibration campaign we started at UC Berkeley. But remember, we're targeting to launch this thing from Antarctica at the end of 2023. We've been approved by NASA for that. They're excited for us. And before we launch, we want to make sure it's going to work. So in June of 2023, we shipped down to NTS in Los Angeles. See, it's very expensive to send things to space, so you better be pretty sure that when it gets to space, it's going to work. And typically, it's much cheaper to bring space down to Earth and put your experiments through what's called a TVAC test. That stands for thermal vacuum. So you take your experiment as much as you can fit and cram it into a vacuum chamber, vacuum out all the air, and then control carefully the temperature in there to mimic the environment of outer space. That way, you'll be able to identify if your electronics will overheat or freeze while the entire system is operating. And you can see us doing just that there. I did say cram as much as you can fit, and you might notice in this image here, our mechanical engineer looking a little bit worse for wear as we realized that we almost did not fit into the chamber. In fact, there were some scuff marks on the top of the chamber left behind by the corners of our instrument when we did this all. You'll also notice down here, our thermal engineer Shun working on controlling all of these white panels. Those don't actually fly with us. Those are heater panels that precisely simulate the thermal environment in space. They were almost all built by my dutiful roommate and colleague Kelsey Yee, who is here seen installing some of them on the instrument from the ground. But needless to say, we did fit the whole thing in the chamber. We did go through our thermal vacuum test. Some of our electronics actually did overheat. But luckily, because we did the test, we could identify those problems and rectify them. So by the time we were ready to leave NTS, we actually had plans for a fully functioning instrument that could survive space. We also, while at NTS, got some bad news. COVID had actually made its way all the way down to McMurdo, which is kind of shocking if you think about it. It's the most remote place in the world. It's very hard to get there, but it had shown up, and it was bad enough that it shut down that year's balloon campaign. And that stranded a couple of balloons down there, which then would have to launch the next year, which meant that we couldn't go down to Antarctica that year. So instead of continuing our journey on to Texas, we flew all the way back across the country to Nevis Labs at Columbia University. This is where we finally actually fully assembled the instrument with all of our flight electronics, and you can see what it looks like before you've put on all of the insulating foam we need to work in space, so it looks much prettier, with one of our electrical engineers next to it for scale. One of the really cool things about Nevis Labs, if you guys ever have a chance to go down there, is that it's a very storied facility. It's a lot of projects have gone through there, different space telescopes, many balloon missions, for a while, the most powerful particle accelerator in the US. And so they have all over the place these walls of Polaroids from old experiments. And so one of my advisors, Dr. Kirsten Perez, demanded of me that I buy a Polaroid camera. And we passed it around and took tons of photos. So now there lives there a stack of photos from our time, our joyful time at Nevis, building and calibrating the instrument. This was also great for me because if you've been keeping track at this point, for more than a year, I've been away from New York. I got a call one morning telling me after I'd recently moved into a new apartment that they needed me at Berkeley in September. And so I got on a plane to Berkeley 3 days after that, and I didn't return home until July of 2023. But there I did put the experiment back together. We did a long and extended calibration campaign before finally being approved again to go to Antarctica. And in May of 2024, heading down to the Columbia Scientific Ballooning Facility. Not to be confused with Columbia University. This is Columbia after the space shuttle that exploded over Texas. It's a NASA-operated facility that validates and confirms that balloons will work before we launch them, and also provides a lot of the critical support staff to make it possible. A few major things happened at CSBF. First of all, you make sure you're compatible with all the telescopes and satellites that you use to control the actual experiment. So you hook it up to the antennas for the first time and make sure that when you tell the experiment to do something, the satellites can actually tell it to do something, and vice versa. Thankfully, we could do that. And the second, more gut-wrenching thing is you do a final weigh-in of the experiment to make sure that when they hook it up to a balloon, the balloon will actually sail off into space rather than sinking down to the ground. And for that, they have to hang the entire experiment from a crane, which is what you're seeing right here. And let me tell you, at this point, when you're more than 2 years deep into tirelessly working to build something, it is pretty gut-wrenching to see it dangling from a thin little wire. But needless to say, it survived. Came in, weighed in at about 5,800 pounds. It's a heavy, heavy thing. Surprisingly, does all go up on the balloon. And again, just a nice little photo, family photo of all of us there at CSBF. Again, not the entire team, just those who could be in Texas when we decided to take this photo. But finally then, it really is ready. No more COVID in Antarctica, or at least none that they know of. They don't test people regularly down there. And so we pack everything up once again into containers and ship it all the way down to Antarctica, which takes about 3 months. So in August of 2024, the experiment, not people, traveled to Port Wenemy, down to Christchurch, and finally to McMurdo in Antarctica. We follow shortly after, and in November of 2024, all of us, scientific payload and people, arrive. This is the view from getting off the airplane. You can't quite see it because it's out of frame, but this forklift right here is actually lifting one of our 20-foot shipping containers filled with the experiment and tons of equipment out of that plane. In the background behind the airplane is Mount Erebus, which is the southernmost active volcano, which does very often erupt, though never severely enough to really endanger people, thankfully. But it does loom large behind you when you're out there at the balloon facility. This is the view outdoors from the balloon facility. You sit out there on a vast expanse of on the ice shelf, the Ross ice shelf, which is basically a flat, endless expanse of ice all the way around you, except for the very distant mountain ranges. It's a stunning and beautiful place to work. This is it when the weather's nice. This is it when the weather's less nice. And we're about to talk about weather a little bit more because it turns out weather in Antarctica is a big problem for balloon missions. But before that, a little bit about what it actually is like to build GAPS. So these are some time lapses we put together of our time down there. This is inside of one of the high bays, and you can see kind of how cramped it is. Space is an absolute luxury here. We got really lucky. We were the only balloon mission to make it down to Antarctica this year, and so we were actually able to use both high bays, which means there's an entire second building filled with stuff. You'll also notice in this moment, everything stops for a brief window of time. That's because down at the balloon facility, you have some of the best chefs on the entire base. And so every day we had to have a religious lunch to make sure that morale stayed high because the days were long and grueling. But needless to say, this is a lot of what it looks like to actually work around in the facility, cramming around people, putting pieces of your instrument together, attaching and cable routing. And then critically also, this is what it looks like when you're finally ready to fully assemble the instrument. So previously you saw the umbrella and eBay, but the mid-frame, which is the middle and center piece of the instrument, was hiding in the other high bay because we couldn't fit them all in here at once until we were absolutely ready to put them together. And so typically what we do here, and what we need to do, is stack everything one at a time on top of it. This is done, thankfully for us, by the rigging team from NASA, who are incredibly skillful and invaluable members of our team. Without them, none of this would be possible. But that is the experiment coming together at the balloon facility down there. And finally, 2 months into this, we were ready to launch the experiment. More calibrations were done. We showed up 6 times to try and launch the balloon, and the weather was never good enough. This is our 7th attempt, which was on New Year's Day. So this is January 1st. And finally, the weather was good enough for them to fill up the balloon. This balloon is 40 million cubic feet. It's filled with helium. And when it launches, this balloon steadily gets bigger and bigger as it gets higher into the atmosphere until it's the size of a football stadium. This is what it looks like when it launches. It's an incredible sight to behold. And I cannot describe how exciting it felt to be right there about to send off this project that at this point was, 5 years of my life had been put into this thing. In some cases, literally consuming my blood, sweat, and tears. But unfortunately for me and sort of all of you as well, this video is going to cut off before the balloon gets released. You see, there's not a lot of infrastructure in Antarctica, so this entire launch takes place on top of a launch pad made from compacted snow. And for a few days prior to this, it had been a little bit too warm. And the launch vehicle, the crane that you suspend your payload from, had sunk into the ice a little bit and gotten stuck. And in order to safely launch a balloon, that vehicle needs to steer around to point your payload in the direction of the wind. And if it can't do that, you can't launch the balloon. So we slowly deflated the balloon, cut it down, rolled back inside. After this, we went outside one last time to try and launch it, but the weather was bad once again. And at that point, the stratospheric winds had actually turned against us, and we had to call it quits. So now the entire GAPS payload sits down in Antarctica, strapped to the walls of the high bay it's in, which have to be driven up onto snow berms to survive the winter. It's chilling down to minus 55 degrees Celsius, which I'm afraid I don't know what it is in Fahrenheit, but I don't really know how much it matters at that temperature. And we are all now gearing up to once again go back to Antarctica this winter to try it all again. And yeah, that is GAPS. So thank you all. Do you guys have any questions?
Gabriel, could you explain how, when you launch the balloon, explain why you do it in Antarctica too, just because of how the weather works. If you could talk a little bit about that.
There's a couple of reasons why you launch a balloon from Antarctica. A few very special things. One of them, the sort of basic science reason, is that we are looking for charged particles, and so those get funneled by the magnetic field down to the poles. That's why you see the aurora. And so we're much more sensitive to particles we care about if we're launching from the South Pole or from a pole rather than from the equator. The other thing that's really nice about the poles is that above them every single year, you form these very strong stratospheric winds that circle around the continent. So if you launch a balloon into those winds, you have great control over where it is at all times and where it will eventually crash when you pop the balloon. And that's important because a project like GAPS is a huge investment from NASA and I guess by extension from the taxpayer. And you can recover a lot of that investment by picking the wreckage of your experiment up off the ice, rebuilding it, and launching it again. So we actually plan to launch this exact payload pretty much 3 times, granted refurbished and rebuilt every time. But there are tens of millions of dollars worth of detectors that we custom built that we want to pick back up. And if you launch that from somewhere around the equator, who knows where your payload winds up? More likely than not, it crashes into the ocean and can never be found again. But in Antarctica, and pretty uniquely in Antarctica, you can guarantee you're going to drop that somewhere over land where you likely can collect it.
Is there a standard amount of time that it's airborne? Like after a launch, do you know exactly when it's going to come down?
You typically think about it in terms of how many circumnavigations you do, each circumnavigation taking somewhere between like 15 and 20 days. And then there's a few distinct regions where they want to pop the balloon because it'll put it in places that are convenient to recover. But it's not always, it's never super clear exactly how long you'll be up there. It depends as well very strongly on how heavy you are, how much gas is in the balloon. So there's a lot of factors. The longest flights have been something like 55 days, and the shortest flights are something like 5. It really depends on the weather conditions and a few other things.
Obvious, but why the upper atmosphere?
We'd actually like to get as high as possible in principle, but most cosmic rays don't reach down to the surface, especially cosmic ray antiparticles. So an antideuteron that's coming from space would never make it down to the ground. It annihilates in the upper atmosphere long before it reaches us.
And why you don't do it in the Arctic instead of the
There are Arctic balloon launches. Actually, the team we work with, they basically travel up and down across the globe every year. They go into Sweden to do balloon launches for NASA and the European Space Agency. But the problem with the Arctic is that nice little polar cyclone will take you right over Russian airspace, and Russia's not too happy to have you fly a balloon over that airspace. So even though in principle all of the reasons why you would go to Antarctica would also bring you to the Arctic, geopolitical conditions are unfavorable for scientific balloon launches there.
Anti-neutrinos, has anybody ever detected one? You didn't quite mention that. And what is considered a mission success how many do you expect to get over a period of time as you fly this?
So no one's detected antideuterons yet. Yeah, we can actually do there's a few antiparticles that GAPS can detect, and AMS in principle is also able to, but they have yet to report a detection of any antideuterons. They have reported the detection of antihelium, which is even more exotic and out there, but so much so that it's actually unclear why we would be seeing those at all. So it's not yet really a dead set thing for dark matter. And we're excited to be a potential follow-up there. So no one has yet detected the antideuteron. There's no clear evidence of dark matter out there, but success for us looks like at minimum 3. So I said its odds are basically 1 in 1,000 that any individual antideuteron is dark matter rather than your background. So 3 reaches us to that golden 5 sigma significance level. That's the standard for claiming a detection in particle physics. So if we find 3, we can say for sure there's something to find. But from there, there's gradations of how excellent your detection is. And as you get more and more, you start to be able to seriously constrain what dark matter models could possibly explain the signal you see. So with just 3, you know there's something more to find. With a few more than that, you can start to really pick apart all those theories I mentioned earlier, and a lot of them stop being compatible with the signal you've observed.
Thanks.
So the AMS that you mentioned is satellite.
It's on the International Space Station. So yeah, pretty much.
Similar designed experiment?
No, so it has very different design constraints. It uses the tried and true tested particle identification method of having a giant magnet, which is great for particle ID because charged particles travel in opposite directions based on their charge, and the exact circular trajectory they take is defined by the charge to mass ratio. It's a really tried and true method. The problem with that is that it's something you can only really afford to do if you're being put into orbit or on the ISS, because that giant magnet takes up so much of your mass and geometric budget, you lose sensitivity. So most of the particles that AMS sees are going to smash into the magnet and never get detected at all. But AMS has been up there for more than a decade, so it doesn't really matter that they're a much smaller experiment than GAPS in that sense, because they have 10 years rather than 30 odd days to actually gather data. And so, yeah, it's a different detection mechanism. It works very well, but you do need to be in orbit, and it's also very expensive to launch magnets into space.
So the anti-deuterium is not dark matter.
No.
You think that somehow dark matter creates it?
Yes. So the basic model is, I mean, we've long since stopped really talking about, you know, specific models of dark matter because there are so many of them, but we generically think that dark matter will interact with other particles of dark matter, and in those interactions either annihilate or also individual dark matter particles could decay. The reason why we suspect that that is true is a little bit beyond the scope of what I can describe right now, but needless to say, we do expect to see these signals from dark matter. And it doesn't just have to be antideuterons. As I said, it could, you will maybe see some positrons, you might see antiprotons, you might see gamma rays. But the issue with those signals is that there's a lot of background to them. So really the focal point of the antideuteron is it's actually a kind of generic signal. You would expect with the antideuteron many other signals, but none as clean as the antideuteron because there's no background for us to worry about.
Dark matter responds to gravity, right?
Yes.
So why doesn't it collapse into, to quote, dark stars or other things that we see in normal matter?
The thing that governs the collapse of matter, you will collapse down to a certain point, but you then need to start sort of interacting, right? So like if I start crushing normal matter together, at some point it gets sticky. It starts, you drive chemical reactions, you drive things like that, you create dust and gas. But if you just had this diffuse material that doesn't interact at all, it never starts to stick to itself or accumulate into the larger, more dense things you would need to drive any of that. So you don't get the same thing you do, even with like a diffuse gas like hydrogen. You have, you know, van der Waals forces that cause hydrogen to actually preferentially stick together. If you didn't have van der Waals interactions for hydrogen atoms, they would behave just like dark matter and form a totally diffuse gas that never clumps up. So if you just, and all those interactions that drive that for ordinary matter really is electromagnetic forces. They're the only thing that sort of has the range and strength to actually cause stuff to stick together properly.
So when we know so much about this already, and we haven't found anything.
Yep.
Yeah.
It's one of the greatest mysteries, and it's
Yeah.
85% of the mass budget of the universe.
Looking for another planet somewhere, and there were projects all over the place waiting to publish there. How many projects are now looking for dark matter?
That's a good question. It depends on where you draw the cutoff, what you define as a project that's looking for dark matter. So I have a lot of friends who work technically in dark matter detection, but really what they're doing is developing instruments that might be able to in the future. So you might classify what they're doing not as dark matter detection. I think there are probably hundreds or thousands of those. In terms of major projects like GAPS, where there's a very real chance of an actual detection happening, there are dozens, I would say. Yeah.
All around the world.
All around the world. We're as far as I know, the only sort of current balloon project that's happening. There are a few balloon projects in the past. There's of course AMS. There's also, I mean, for a project like AMS or like Fermi, these things can be dark matter experiments, but it's not their only purpose. But something like GAPS or Xenon, they are only dark matter experiments. So the actual accounting can be quite hard.
They share data.
They share results. In principle, once we have launched, once we have then succeeded, we'll have a rich array of data, and we'll share the ultimate final spectrum that we measure, the cosmic ray spectrum of antideuterons, which will be a useful constraint anyone can use to compute, to measure up their models. But it's pretty uncommon in particle physics to share the raw data, if you will, of the experiment. But the process results, of course, are public knowledge.
A little bit at dinner too. So after this, if you have some success with this, or even if you don't have success, There's that science too, obviously.
Mhm.
But if there's not, what would be the next step? What would be the next generation of gaps?
Yeah. So as I mentioned, we are currently funded for 2 flights and plan for a third. So the first step for us is just to launch the same experiment a few times, maybe make a few upgrades along the way, slight tweaks to things to improve its overall performance. And from there, if we've actually discovered shockingly, a few or dozens of antideuterons and have really made some kind of measurement, there is then a massive open hunt, I think, across the entire scientific community to design an experiment that can measure that with increasing precision across a greater energy range. And some of those will look like larger balloons. My advisor has sometimes joked about launching 3 different gaps in one season. So we have 3 of these floating around, which for anyone who's actually tried to build this is probably causes the blood to drain from their face. But you could also go for a satellite of some kind, which would be a smaller, less massive experiment, but have, of course, the advantage of being in orbit for decades potentially. It's unclear exactly what we would come up with that would be the best way to search for this, given the kind of resources that would be allocated if it was a successful detection, since it would be the only detection at that point of a signature of dark matter.
Budget?
Right.
Budget's a hard one because
I know it's been spread out over 20 years, but
it's a hard one because whenever I ask my boss, the number gets bigger. Which of course part of it is, the budget gets larger as time goes on, but not that much larger as time goes on. It's spread out over a long time and also over many different funding organizations. So we have collaborators, we have JAXA, we have a lot of collaborators in Italy at INFN and also OSI, which is the Italian space agency. Of course, we have NASA and NSF at home. We typically talk ballpark $30 to $50 million. It's a lot for a balloon.
I understand.
Yeah.
And risk because of this year.
Like how likely do you think we are to launch next year?
Survive with a budget.
Oh, well, we will launch next year, and no idea what happens after that. The conditions of the federal government have deteriorated, of course, but I have one colleague who's, when she complains about the uncertainty, her dad just says, well, you don't have to look for a job for another 6 months, so what are you worried about right now? And that's the kind of Zen attitude I'm trying to have about the whole thing. Mm-hmm.
Other one was, do you know what altitude you're expecting the balloon to fly and for how long you're hoping?
We typically think about 30-day long, 3 30-day-ish long flights, but that's based on kind of the median expected flight. Longer is always better, and as I mentioned, sort of the longest balloon flights are 55 days up to. It depends entirely on the weather conditions. We will go for as long as possible or as short as we're allowed up to a point. We typically say that 10 days is our sort of flight minimum. If you can't launch us for more than 10 days, there's not that much point to even launching in the first place at all. But that's adjustable depending on conditions. And then, wait, sorry, the other question was altitude. Oh, I always forget the exact number. I'm going to say off the dome like 120,000 feet, but I might be getting a feet and meters conversion confused somewhere. But it's pretty way up there. Might be 150,000 feet.
Potential contenders, is modified gravity still in the mix? And could you maybe give the Cliffs Notes version of black holes or primordial black holes as an explanation?
Definitely. Modified gravity is sort of still in the mix. It's a hard theory to fully shut down. It currently does not do as good a job of explaining as much evidence as a particle theory of dark matter does. So it's not underwater, but actually one of the major challenges it has is explaining the CMB and also the bullet cluster. Those are 2 major tokens on the side of particle dark matter. But it's a field rife with conflict all on the theory side. Of course, if it is modified gravity, there's no signals you can find with an experiment like GAPS. But I don't think anyone has a very good idea right now of clean signals you can find for MOND in general. It's unclear, but the current state of affairs is that particle dark matter theories do explain more of the available evidence and do a better job of it than any competitors. And then the second question was black holes. Primordial black holes are black holes that form at the very beginning of the universe. They form through different mechanisms in the stellar black holes we know of today. They could explain dark matter because if you had a flurry of small black holes, you might not be able to detect them with more normal techniques. They have been ruled out in many different regimes. So the space that's available for primordial black holes is narrowing. But there are still, if you have black hole masses in the range of sort of mountains to planets or moons, there still is an open window for where you could have where it could explain all of dark matter. There's ongoing efforts that are mainly based around improved precision measurements of of stars and looking at galaxies for specific signals you might expect. Interestingly enough, GAPS is also sensitive to some primordial black hole models, because if you do imagine you have primordial black holes from the early universe, they are evaporating slowly. And today, they might be near the end of their lives and would produce, in those evaporations, a lot of exciting and exotic particles. And one of the other things we're sensitive to that we expect to measure is the antiproton spectrum at low energies, which would be sensitive to certain models of primordial black hole dark matter.
Like 40 minutes.
About
40 minutes.
modified gravity.
40 from now.
We looked at this from studying the angles that we're pretty sure there's something that we can't see that has mass.
Yes. Yeah. People who believe in MOND are very, they really believe in MOND. And I think they don't have necessarily bad arguments, but again, the most evidence and the best explanation of that evidence still comes from particle dark matter. The MOND theories are increasingly convoluted and struggle to explain everything we observe.
Impressive, very impressive.
All right.
You guys very much.